So now for radicals and surds. To start off with, we're going to have to cover some terms. This here is the radical. This here, the number above the radical is the degree, and the number which is underneath the radical is the surd. Radicals and surds follow some certain rules. For example, if you take this radical here, one radical with nothing is essentially just the square root. So if you square a radical, it will essentially automatically become the surd without the radical. If you multiply a radical with its surd with another radical of its surd, for example 5 squared, or square root of 5 times square root of 5 here, it becomes the square root of 5 squared and just becomes 5. The same also counts for negative square roots. So negative square root of 5 times negative square root of 5 becomes 5. This also counts for the cube root of different numbers. For example, here we take a. A is a real number, but when you have a cube root, you'll have to multiply the same thing 3 times, meaning you have to cube a number to turn it into a full number. Some of the properties of the square roots include that if you have two surds which are multiplied underneath a radical, you can separate the two like this, as long as the surds are equal to or greater than 0. The same goes for division. So as long as they are greater than or equal to 0. The properties of radicals are they follow all the same algebraic rules like all other numbers, and they essentially just act as variables. So you can pretend that if you have an algebraic rule and you wish to use it, you can essentially just replace a with the square root of 2, like this one here. We're using the distribution rule, where you use the square root of 2 instead of a and the square root of 3 instead of c. Square root of 2 times the square root of 2 equals 2, and the square root of 2 times the square root of 3 equals the square root of 6, because as you see up here, if you take two square roots and multiply them by each other, you simply put them under the same radical and then multiply them. For one concept which is special to radicals and surds is that you have the simplest radical form. This essentially means that you try to remove all radicals and surds from an equation and don't have any radicals or surds as a denominator. One way of doing this is with this example here, where you take 1 over the square root of 2. The way you would remove the square root as the denominator is you would multiply it by the square root of 2 over the square root of 2, meaning that you take 1 times the square root of 2 and square root of 2 times the square root of 2, and that turns into square root of 2 over 2. The reason you can do this is because you're essentially just multiplying by 1, since the square root of 2 divided by the square root of 2 is 1. So you're not changing anything on any side of the equal sign. Now, for addition and subtraction of roots, it's actually quite simple. You essentially just try and add a number of different roots together. So for example here, you have 6 square roots of 2 plus 3 square roots of 2. You can use factorization to see that these two have the square root of 2 in common, so you can put 6 and 3 in parentheses. Then you calculate that, and then you get 9 square roots of 2. You do the same thing for subtraction. So 9 square roots of 2 minus 7 square roots of 2 equals 9 brackets 9 minus 7 square roots of 2, which equals to 2 square roots of 2. Now, as mentioned earlier, when you have a root, it essentially acts as its own variable, meaning that you could replace it with essentially any letter. The only difference is that they have the extra properties of being a root, meaning that, for example, if you have the same root squared, you end up with having whatever the surd is. So this means that, for example, if you have five square roots of 2 and 3 square roots of 3, you essentially cannot add these two together because uh, they're both different roots. You can imagine this as having 5a plus 3b, and obviously there's no way of adding those because those two are different variables. So that's what you do when you try and add or subtract this two different roots. So when you're multiplying roots, however, it's quite possible to multiply roots with different surds. So in this case, for example, we're multiplying 5 square roots of 2 by 3 square roots of 3, which equals to 5 times 3 times square root of 2 times square root of 3, which then can be reduced to 15 times the square root of 3 times the square root of 2, which is then finally reduced to 15 square roots of 6, using the rules that we learned earlier. The same goes for division. So, for example, here you have 6 square roots of 6 and 3 square roots of 3. This can then be reduced to the 2 square roots of 2 and 1 square root of 1, because when you divide 6 by 3, you get 2 and 1. And when you divide 6 by 3 again, but it's under the square root, you get 2 and 1. So you get the square root of 2 and the square root of 1. Now for proof that the square root of 2 is irrational. The way we're going to prove this is proof by contradiction, which means that you're going to try and assume that square root of 2 is rational and some way create some mathematical nonsense, which essentially means that it makes no sense for this rule to be true or untrue, or that it's a mathematical operation that will loop forever. So we assume that the square root of 2 is rational, which means that the square root of 2 is equal to p divided by q, where p and q are both integers and q is not equal to 0. We also assume that p divided by q is irreducible, so there's no way of reducing it. First, we take the square root of 2 and square it, and also square p and q. So we end up with 2 equals p squared divided by q squared. Next, we rearrange it into p squared equals 2 times q squared. We're essentially just using algebraic rules and moving the p over to this side and moving the 2 over to this side. And now we can see that p must be even, since q squared is an integer. And this is because if a number is divisible by 2, that means that it has to be even. This is why, you can see this because p here is divisible by 2 because p is equal to 2q. Then you can transfer this into just p being equal to a random variable, which we will call k. So p equals to 2k, where k is an integer. Now we can say that p squared is equal to 2q squared, which means that 2k squared equals to 2q squared. Now if we reduce this, we can say that 4k equals to 2q squared. This means that q is equal to 2k squared, where k is an integer, which means that q squared is even, since k is an integer, and you can see here that q is divisible by 2. So we can say that q is equal to 2l, which is just another random variable, which is also an integer. So this means that the square root of 2 is equal to p divided by q, which is equal to 2k divided by 2l, which doesn't make sense because p divided by q is supposed to be divisible. So if you reduce this, you would just end up going through the same process again, and it would continue forever.